In today's notes, we're going to be discussing solution strength and solution stoichiometry. In the previous set of notes, we discussed various vocabulary that involved descriptions of solution strength. The difference in what we're going to be talking about today is that we're going to be doing calculations involving solution strength. So the first calculation is percent mass. And in a percent mass calculation, you take the mass of the solute, divide it by the total mass of solution, and multiply it by 100. So let's work through an example. If 324 grams of sugar are dissolved in 1 liter of water, what is the percent mass? Well, when we look at the percent mass, we know that we're dealing with a solute and solution. And we know that a solution is made up of a solute and a solvent from our previous set of notes. So it's easiest if we can assign what is the solute and what is the solvent. So our solution here is made up of sugar and water. So sugar is what gets dissolved, so that makes it the solute. And water is what does the dissolving, so that's going to be the solvent. And our solution here is made up of solute plus solvent. So when we're percent mass calculation, we need to know the mass of our solute. So percent mass is going to be the mass of our solute. Well, our solute is our sugar, so we have 324 grams of our sugar. And we're going to divide that by the total mass of solution, which is the solute plus the solvent. Well, the information we're given here is that we have 1 liter of solvent. That's a volume, not a mass. So how do I change that to mass? Well, from previous information in the class, we know that 1 liter is equal to 1,000 liters. And from this, and this, by the way, this is only for water. This doesn't work for other substances. We know that 1 milliliter is equal to 1 gram. So by logic, 1,000 milliliters is going to equal 1,000 grams. So 1 liter of water will equal 1,000 grams of mass. So now we have a mass of our solvent. So we have 1,000 grams of solvent, 324 grams of solute. We add those together and we get 1,324 grams of solution total. Then we need to multiply it by 100 because it is a percent. And when we punch that into our calculator, we should get 24.5%. And there is our answer of the percent mass of that solution. The next type of solution strength calculation is something called molarity. This is not to be confused with just moles. Molarity is the moles of solute divided by the liters of solution. It is not the liters of solvent, it is the liters of solution. Okay, so let's do an example problem. So what is the molarity of a solution made by dissolving 324 grams of sodium chloride into enough water to make 2.3 liters of solution? So first of all, we're given the 324 grams of sodium chloride. And again, we should be finding what's our solute, what's our solvent. The sodium chloride is going to be our solute, because that's what gets dissolved, and water will be our solvent, because that does the dissolving. So we need to know our moles of solute. Well, I'm given grams of solute, so that means that I need to convert these grams to moles. So we do 324 grams of NaCl, time sign in a line, put grams on the bottom, moles on the top, and 1 mole of sodium chloride weighs 58.45 grams, which when we crunch that out, we should get 5.54 moles. So now we have moles of solute. So now we can put in molarity is equal to 5.54 moles divided by our liters of solution. And here we're told that it's 2.3 liters of solution, so we don't have to add anything together this time. So it is 2.3 liters. And when we divide that out, we should get 2.4 molar. So when we're using molarity, we are represented by a big M. And the big M is the same thing as moles over liters, and that's going to come in handy in just a minute. So the units are the same thing. So moles over liters, you can substitute in a big M. You can also take this big M and break it into moles over liters. And now we're going to move into stoichiometry with solutions. So the key with stoichiometry with solutions is we need a conversion factor that for volume and for moles. Now we can't use Pivnert like we did in gases because we're not dealing with gases here, we're dealing with solutions. So we have to use a different conversion factor. And what we're going to be using is molarity. So molarity can be used as a conversion factor between moles and liters of solution. Notice that it's only of solutions that we can use molarity for. Okay, so and the reason we can do this is because of what I just talked about before, is that molarity is equal to moles over liters. So if I have a 5 molar solution, that means that I have 5 moles for every 1 liter. If I have a 3.78 molar solution, that means I have 3.78 moles for every 1 liter of solution. And we're going to use this in the next example. So we're given an equation, it's already balanced for us, and we're asked what mass of barium chromate will form from 205 milliliters of 0.75 molar potassium chromate. So where do we start? Because we have 2 pieces of information here, but they're about the same substance. So it's not 2 calculations like we would have with a limiting reactant problem. So, well, if we look, we just said that molarity, this is a conversion factor. The volume is not a conversion factor. So we're actually going to start with the volume. So you always start with volume. That's going to be a big key. So where do you start? You start with volume. So you start with your 205 milliliters. Now, this 0.75 molar we said was a conversion factor. So what that really means is that it's 0.75 moles over 1 liter. So in order to use this conversion factor, we need to change our milliliters into liters. So we're going to use the piece of information we used earlier in the notes, that 1,000 milliliters is equal to 1 liter. So that's going to cancel out. And now we're in liters of K2CrO4. And then we're going to change from liters to moles, because we need to change substances, so we need to get to moles in order to do that. So for 1 liter, we have 0.75 moles of K2CrO4. And then we know that there's 1 mole of K2CrO4 for every 1 mole of barium chromate. And then we need to get to mass of barium chromate, so we're going to go from moles to grams. And 1 mole of barium chromate weighs 253.33 grams. So our liters cancel out, our moles of potassium chromate cancel out, our moles of barium chromate cancel out, and we're left with grams. And when we crunch all of our numbers and we consider sig figs, we should get 39 grams of barium chromate. So one thing to note is that molarity does count towards sig figs. And we're going to move on to another example. This is a similar example. So what volume of 0.38 molar barium chloride is needed to make 10.2 grams of barium chromate? Again, we're given two pieces of information here. But like we said, molarity is a conversion factor. So we're going to start with the piece of information that is not a conversion factor, and that's our 10.2 grams of barium chromate. So we start with 10.2 grams of barium chromate, and we're going to convert that to moles because we're looking for volume. So we need to get to moles to change substances because barium chromate is a different substance than barium chloride. So grams to moles, and barium chromate still has 253.33 grams per 1 mole. And then we know that there's 1 mole of barium chromate for every 1 mole of barium chloride. And then, so we need moles of barium chloride on the bottom. And on the top, we're looking for volume, so we're going to go right to liters. So, this is an L. Okay, so we know that from our conversion factor here of the molarity that we have 0.38 moles of barium chloride for every 1 liter of barium chloride. And our grams of barium chromate cancel out, our moles of barium chromate cancel out, our moles of barium chloride cancel out, and we're left with liters of barium chloride solution. And when we crunch those numbers out, we should get 0.11 liters of BaCl2. And we're going to move on to our last example. In our last example, how many moles of barium chromate will form when 3 milliliters of 0.5 molar barium chloride is mixed with 275 milliliters of 0.45 molar potassium chromate? Let's look at our pieces of information again. We're looking for moles of barium chromate, so we'll put that in our box. Will form when 3 milliliters, that's a volume. 0.5 molar, that's a conversion factor. 275 milliliters is another volume, and 0.45 molar is another conversion factor. So we have 2 conversion factors and 2 volumes, and we're dealing with 2 different substances here. This tells me that this is a limiting reagent problem. Or limiting reactant. So that means we're doing 2 calculations. So I'm going to start with the barium chloride. And again, because we don't start with conversion factors, we're going to start with the 3 milliliters. And we're going to convert from milliliters to liters. Milliliters will cancel out. And then we have liters on the bottom, and because we need to change from barium chloride to barium chromate, we're going to go get into moles so that we can change substances. And we know that 1 liter has 0.50 moles from our molarity over here. That's BaCl2. And for every mole of BaCl2 that we have 1 mole of barium chromate. And that is going to give us 0.0015 moles. But we're not done yet because we still have to figure out how much barium chromate can be made from the potassium chromate that we're given. So start with our 275 milliliters. And again, we're going to convert from milliliters to liters. Cross those out. And then we're going to go from liters to moles of K2CrO4. And in this case, it is 0.45 moles per 1 liter, and that's from our conversion factor of our molarity. And then we have moles of K2CrO4 and moles of barium chromate. And from our balanced equation, it's a 1-to-1 ratio, so it's 1 to 1. And that gives us 0.12 moles. And because we don't have enough barium chloride to make any more than 0.0015 moles of barium chromate, the barium chloride is our limiting reactant, and we're going to end up with only 0.0015 moles of barium chromate. Hope that all these examples have clarified solution stoichiometry as well as our two types of calculations for the solution strengths. If you have any questions, please ask, and good luck with your calculations.